Maybe after some or 10
I mean, feel free to get started whenever.
Yeah.
Actually, it's pretty accurate.
So how do people do this? Do they sit or stand or I apologize, I haven't come to any of these.
Up to you. People know.
People have done both?
Yeah.
Okay, I'll stand. But yeah, just for a sense of like terminology and stuff, how many of you have heard of a light curve? Good, all right, cool. You know, it's mostly theorists, but I'm going to be saying that a lot. And magnitude, like an optical magnitude. Good, all right, yeah, just remember, brighter is a lower number. That's the one thing to, and I've run into trouble with that in the past. Okay. I'll sit. I like sitting actually for this talk. So the motivation for this talk is purely data driven. So I'm going to talk a lot about statistics, a lot about data, and I really want everyone's input, especially toward the end. So the motivation for this comes from mainly from the Zwicky Transient Facility, ZTF. It's a robotic telescope, and it images the whole sky once every 2 days. So what it's done, and this thing is owned by Caltech, sits about 3 hours away from here at Palomar, on a mountain, and it's looked at the whole northern sky for the last 5 years, since March 2018. So a lot of people have put in a lot of time into looking at data from this telescope, but the biggest effort is looking at things that are new, at transients, at things that explode. So because of that, a huge group, like 90% of the collaboration is involved in that. And I'm part of the 10% that looks at things that are persistently variable or maybe not variable at all. And the kind of problem that's come about is that there's just so much data from this now. And the color bar you can see here is in some patch of the sky, how many points are there in a ZTF light curve? So the average is like 700 points, but it can get all the way up to 1600 points. So not only do you have like the whole sky of coverage, but you have all this time coverage. To add to the complexity, it also looks in 3 filters, R, G, and I, mostly R and G. So you could do like a whole color analysis. And the biggest thing that people ask me is, why don't you just run a machine learning classifier and everything and figure out what everything is? It's not that easy. The machine learning group has tried that and they've done versions of it, but you need a very reliable training set. If you want to discover new things, there's all sorts of, anomaly detection, but you still need a training set for that. Like there's no way to just automate that completely. So in total, the number of light curves from ZTF at the latest data release is there's 1 billion light curves with more than 20 points. So some are just really faint objects that don't have much coverage. That's how you can get up to 2 million, or sorry, 2 billion. 2 billion can have a couple of points, 1 to 5. But if you're looking at persistent sources where you can actually track it over time, determine if it's been erupting, if it's periodic. I'll talk a lot about periodic sources as well. The good number for that is that it's starting to approach 1 billion.
How often is it?
On average, it's supposed to be once every 2 days, but
During the season.
exactly. So during the season when it's up. But for those where you only have 20 points, that means it's really faint. So conditions have to be good. It has to be high enough in the sky. So for those in practice, it's not once every 2 days. So it could be, once every, for 5 years, for 20 points, right, the lower limit is 5 divided by 20.
Seems like at this point, you feel like how many of more than 200 points? Like 20 makes sense when we're compared to 0. Yeah, that's just.
Yeah. And I guess the good number for that is the average of everything is 700. So yeah, the average light curve is 700. Let's say a couple 100 million have around that number.
So why is it that R has the most? Is it like easier to see things in R or something?
Yep. So it's predominantly because of galactic dust. extinction. So if you want to look along the plane, most of the stars in the galaxy are in the plane. So the G band, you can get it for a lot of them, but once you get close enough to the galactic plane, it'll attenuate all of the G and you're just looking at R.
So why not I?
That filter is a little bit more, it's less sensitive. The throughput is lower, and the calibration images for that, it just never really took off. Yep. And the thing that should worry a lot of people, and this is what worries me, is that's ZTF, that's the current optical time domain gold standard. That's going to change very quickly, really next year. So ZTF was always built as kind of a predecessor to the Rubin Observatory. ZTF is on a 1.5 meter telescope. This is going to be an 8-meter telescope. And remember, that's the diameter. What matters is the collecting area. So that's squared. 64 divided by 1.5 squared. You do the math. And it's going to be a 10-year-long survey, not just the 5 years. ZTF will probably operate for longer, but let's say it just quits at 5 to 6 years. The funny thing about LSST is it's going to have less, it's going to have a less dense observing pattern. It'll scan the whole sky basically once every 8 days in a given filter. So if you look at the number of points per light curve, it's about the same. The maximum is about a couple thousand. But if you look at a table that compares these all sky surveys, the really worrisome thing is that, ZTF, I said, looks at a couple billion, 1 or 2 billion objects. LSST is going to look at almost 40 billion objects. So that's a huge factor. It's a factor of 10 times as few. And if I already told you that it's too hard to do machine learning on this 1 billion, imagine the 40 billion. All of this is just kind of the final overview of one of these big intractable surveys, and this is Gaia. So what Gaia has done is it's really revolutionized stellar astronomy by getting you precise distances to most stars in the Milky Way. And it's looked at 1.8 billion stellar positions, you can see here. The thing that people really haven't probed a ton in Gaia, depending on what study you've done, people have looked at sources with good parallax, with good distances pretty well, but there's a whole set of sources that have proper motions that you can see that they're moving on the sky, but they're so far away or so dim that Gaia couldn't get you a good parallax. Those can also be galactic sources. Really only in a couple of studies. If you know what to look for, then you'll look at sources that have a proper motion. So hypervelocity stars that are moving really quickly, stars in moving groups, those have been looked at, but the whole catalog of proper motions, it's often ignored. People often impose a parallax constraint. So how to tackle this? These are kind of the main catalogs that I use and that I've sort of explored and can say something about. And what's really encouraging are these multi-wavelength catalogs. So I've been marketing myself as a multi-wavelength astronomer, primarily in part because they're a lot easier to work with because there's fewer objects. So just going from top to bottom, Galax was the latest ultraviolet survey of the whole sky, almost the whole sky. It actually didn't cover the galactic plane. And this has about 10 million sources.
97% of the sky was 70%.
That 97% number is, so it did image the galactic plane. It's just things weren't properly reduced. So if you look at the mass database, I think there are at least detections for 97% of the sky. Yeah. But there's all sorts of quality flags. Effectively, yeah, it's only 70% of the sky that's usable.
And of course, you just got the next generation approved.
Yeah, so that's going to be another big motivation. I'll talk at the end of this set of slides. What can the UV do? What can I do with the UV actually? So 10 million is a lot more tractable than a couple billion. For the infrared surveys for WISE and NEO-WISE, so that's a few 100 million. That's also pretty big. But once you get into the X-ray, the last all-sky X-ray survey from 30 years ago only had a few 100,000, had about exactly 100,000 sources. The newest all-sky X-ray data set that is the subject of my thesis is about 1 million. So the latest, if you download the FITS table that was released 2 weeks ago, it has 1 million sources in it. Basically at the same time, so this was the biggest data release. Sorry, this was the biggest all-sky survey in the X-ray in the last 30 years. Similarly, in the last 20-ish years, the radio has been changed. So there hasn't been an all-sky radio survey that's as deep as the VLA sky survey. And this also has a few million objects in it. So these two are kind of similar, and these are the two surveys that I'll focus on to try to combine with the optical, combine with those billion sources to try to make some sense of those billion sources, try to find the most interesting ones. So I'll begin with the question.
When you say sources, for example, you have 2 billion there and then few million there. Do we have like, so when you say source, do you identify it exactly, or is it like, okay, some point in this direction?
That's exactly what I'm going to talk about in the second half of this talk. So in general, and this is the big thing that I've been working on and trying to figure out. In general, I'm going to assume that the optical is like perfectly well localized. It's not. In most parts of the sky, it's localized to about 1 arcsecond. And just for comparison, you don't need to know exactly what an arcsecond is, but the X-ray is localized to about 10 arcseconds. So indeed, you're seeing something like this, where you could have, this is the 10 arcseconds, and the course, this is in the X-ray. You can have the correct optical source be here. The problem also arises, maybe you have, and this is localized to 1 arcsecond. The problem is if you have something else that's here, or something that's there. Yeah. So, and just as kind of a comparison then with the radio has been reported to be about 2.5 arcseconds.
With the added issue that a lot of radio sources have these huge radio lobes with the core that they may or may not see, and so that it's a mess.
It looks crazy. Like if you look, I have seen some of the images where it like streaks like this, right? And then it has like spikes like that. So whoever reduced these images, they did all the hard work for me in actually localizing that point. That's a good question. That's the second half of the talk. So already X-rays are interesting to me because they trace high energy processes, at least for both extragalactic and galactic objects. Please add any examples if there's something that I'm forgetting, but at least for extragalactic objects, X-rays come from the corona above supermassive black holes in AGN. Galaxy clusters, that's the hot intracluster gas, you're actually seeing that glow in X-rays. And for galactic sources, there are these, it's really just 3 main sources for X-ray binaries. So the only examples, well, not the only anymore, but the majority of the examples of stellar mass black holes in the Milky Way, the disk basically is in so deep a gravitational potential that it gets hot enough to actually emit X-rays. So it's the innermost parts of the disk itself in X-ray binaries that emit the X-rays. However, you can also have accreting white dwarfs. Those are also galactic X-ray sources. That's the majority of the things that I study. There's 2 flavors of these objects. The first is where you have the white dwarf in the center, and you have an accretion disk around it that's being fed by a donor star that's overflowing its Roche lobe. And the X-rays come from so the white dwarf has its own spin to it. the spin of the disk is just the Keplerian speed of the material around. So this is very fast. This can approach like thousands of kilometers per second. The white dwarf is nowhere near that. So the material has to slow down in what's called the boundary layer. It's a very thin layer sort of between the disk and the white dwarf, which emits the X-rays. The other flavor of these systems is where you have a highly magnetized white dwarf, where B is about 100 megagauss. The sun, for reference, is about 1 Gauss. And you also have a donor star overflowing its Roche lobe, but the material latches on to the white dwarf magnetic field, and the field channels it onto the white dwarf, so it slams onto the surface. That emits thermal X-rays. That's just free emission, is the shock onto the white dwarf surface. So those are the two flavors of accreting white dwarfs that are another X-ray source in the galaxy, and then active stars. So the sun, I mean, the sun itself emits X-rays. And a good number to remember is that the Lx over the total luminosity of the sun is, I think, like 10 to the minus 5 to 10 to the minus 7. So it's just a small fraction of the sun's total luminosity, but it's significant. For active M stars, they're the most numerous stars in the galaxy. For those, it can approach 10 to the minus 3. So it can be a lot higher. That's just from the hot corona. There's magnetic reconnection, a lot of flaring events. That's another X-ray source.
It's unusually like low X-ray luminosity.
For its type of star, it's about on par, yeah. Yeah. But compared to the majority of stars, yeah, it's a little low. Right. And there's two ways to go about really any survey. There's narrow and deep versus wide and shallow. This plot is area on the sky that an X-ray survey is covered versus the flux limit, really how deep it went. So the deeper surveys are lower down here, but you'll see all of these very deep surveys. They cover 10 square degrees on the sky. The whole sky is 42,000 square degrees. That's really nothing. And to get kind of a big census of all the objects in the Milky Way, those are just not appropriate. Maybe they're fine for extragalactic surveys where you just want to look through some sort of cone, but not for the galaxy. That's where this eROSITA survey enters the picture, and these sort of dashed lines represent the number of objects per X-ray survey. So you'll see that these very deep but very narrow ones, those have about 10,000 objects. The state of the art before was about 100,000 objects. Now this is about 1 million. So as a final motivation for why to combine the X-ray plus optical, the first stellar mass black hole in the Milky Way was discovered first as an X-ray source in 1964. This was Cygnus X1, and this is the discovery chart. So this is plotted in degrees, just to show it was huge. It was just a rocket that was sent up and localized one thing basically to within a degree, which is a huge area on the sky, actually. 1 degree is really, really big. The moon's half a degree. So yeah, just for a sense, this is about 1/30th of a degree, this patch on the sky. So there's already all of these stars. But it was optically associated in 1971 with this very bright star in the center. And it was a combination actually of optical plus radio. Radio also localized it to one very small patch of the sky. And what was done with this star nearly 7 years later is you can measure as a function of orbital phase what the radial velocity is, so how much the Doppler shift of the star is. And at that point, it's just Kepler's laws to give you the minimum mass of the companion. The minimum mass was determined to like 5 solar masses. There's no type of star that could hide. Like you would also see it in the spectrum if it were 5 solar masses. So it was immediately, okay, this has to be a stellar mass black hole.
Was that the first black hole, or was 3C273 quasar the first black hole?
That was the first extragalactic. Yeah, this is the first stellar mass black hole. So 3C273 is the quasar, right?
First.
Oh, that was 63. So that was first. That was the first black hole. Yeah.
Was that meant to be a black hole?
Black holes weren't good.
Well, yeah, but like, the word wasn't even point. Like, how
No,
long did it take?
no. I mean, this one they didn't believe till 1977, really. Yeah, 3C273 was the lecture in the Feynman auditorium where like Feynman stood up, right, and said, "Oh, it can't be a star." There was some discussion there, right? Like Martin Schmidt presented something there. It's a story that I should know, but this one was doubted basically till 1977. Okay, so I'm going to show a big plot. That's the first really new thing that I'm going to show in this talk. And I'll walk, if you don't recognize all these categories of sources, I'll explain what they are. But this is something that I'm calling the X-ray main sequence. So I'll let you sort of stare at this plot and just tell me sort of what you glean from this in a sec here. So I'll mention a couple of terms here. On the x-axis, this is a blue color minus a red color as measured in the optical. This is a proxy for temperature. So if you've seen the HR diagram, the Hertzsprung-Russell diagram, it's also has an optical color, B minus R on the x-axis, except in that diagram, the y-axis is an optical luminosity. So here on the y-axis, it's the ratio of X-rays to optical light. So the sun sits somewhere down here, right? 10 to the minus 5, 10 to the minus 7. The sun, the majority of its luminosity, the majority of its flux is in the optical. So the sun will sit somewhere down there. So this plot shows all sorts of accreting compact objects up here, basically. In gray are all of the points that come from a cross match of an X-ray survey and an optical survey. In this case, the X-ray survey is good enough that I selected the points where the X-ray is like 2 arc seconds in diameter, like the uncertainty of the position, and the optical is like just 1 arc second. I removed all cases where there's like multiple sources within the X-ray point, such that there's only 1 X-ray and 1 optical. So I consider that to be a very clean catalog in the gray, and in red are all of the accreting white dwarf systems. In cyan are the accreting neutron star systems. That's another neutron star system, neutron star black hole systems, and all of the active stars are below this cut. That then separates into young stars in orange, and then just coronally active binaries or single stars in green. These symbiotic stars, these ones in black down here, those are a little bit trickier to put in either category, because those are a red giant that's donating onto a white dwarf or a neutron star. So those systems, they're very optically and infrared bright. So they sort of bring down, like, or else they would be up here. If they were a main sequence star, they'd be up there. But because it's a red giant, it'll bring everything down here. Whether there's a separation between these and these other active stars, I don't quite see it, because there's still some overlap. You could say that if you look low enough, then those are going to be symbiotics. but it's definitely not as clean as the separation up there. And I'll explain what this theoretical cut is and what the empirical cut is in a sec here, but the whole reason for making that plot is because it's a much cleaner way to separate the sources than, for example, just a typical HR diagram. Yeah.
On the previous plot, how would a perfect black body appear in this, like for very temperature?
Right. So, right, a perfect black body is indeed this theoretical cut line, and that's at a fixed X-ray luminosity. Yep, that's how I constructed that. Yep. Comparing that plot to this one, here you can see that basically all the pulsar and black hole systems sort of merge into the main sequence. They're not cleanly separated. The white dwarf systems are on the whole, on this side of the stellar main sequence, but there's all sorts of these red dots still in there. Most of that is due to the donor star being luminous enough that it just looks like a main sequence star. But if you look at the X-rays, then it'll pull all of them back up. Indeed, here you see that all the giant stars are up here where the giants should be. All of these other stars, these are still neutron star and black hole systems. Again, the donor star is so bright that it'll just get into this mess, and it sort of ties in with some of these other active stars. Like this is the only way to really pull the two apart. Okay, and the reason for why this works, so here is getting into the physics. That's not just, I mean, I motivated it as a data plot, as an empirical plot, but there is some physics behind those lines. Even though the physics is still not fully understood, what has been observed is that for active stars, for the ones where the X-rays are just due to magnetic activity, there's what's called a saturation limit. The maximum fraction of X-rays to the bolometric luminosity that can occur for those stars is around 10 to the minus 3. It can get up to like 10 to the minus 2 like the 2.5. Like this spread is real. A lot of that is due also to flares. These can undergo small flares, small like coronal mass ejections, like the sun undergoes, and those will push it up and down. You'll see that for stars, this is just the rotation period of stars. So the ones that rotate faster tend to not be as X-ray active. And then if you can, spin up a star and make it rotate faster, then that'll saturate the X-rays. That's thought to be tied to how magnetic fields are actually generated in these stars. The dynamo mechanism, similar to so the Earth is a turbulent dynamo. There's also the alpha omega dynamo, which occurs in M dwarf stars. I guess, there's a maximum amount of rotational energy that can be converted to magnetic energy. This is just another plot showing the same thing, but basically just showing the stellar temperature instead of the rotation period on the x-axis. So as a whole, the more luminous stars, the hotter stars tend to be below the saturated point, and it's really only the cooler stars which can reach the saturation limit. And this is then how you convert, I guess, either from a perfect black body or from a perfect stellar atmosphere to that theoretical line. I just said there's this limit of Lx over L bol is equal to 10 to the minus 3 or 10 to the minus 2.5 as an absolute maximum. One can generate these theoretical tracks, which is just an optical color versus the bolometric luminosity. This is called an isochrone, and you can generate this for stars of a given age. You have L bol, we have Lx equals something times L bol. You can literally just convert that to Lx over L opt by getting an optical luminosity from Gaia, just knowing what the conversion is between a Gaia magnitude and an optical luminosity. And that's how I get that line.
Does not actually, you said before that line is a black body, the X-ray is the continuation of black body.
Yep, exactly. Yeah, yeah, that's a good, yeah, it's a great, yeah, great clarification. Yeah, the X-ray can be some fixed number, some fixed ratio in this case. This is kind of a jump, but this is really the main, this is the only part where I try to explain what that limit comes from. But you'll see, just going back to the plot, that it's not that good. Like there's still plenty of active stars above that cut. Looking, I didn't look, it's way too many in the gray to look at by eye, but of the known ones that are above that theoretical line, a lot of them did undergo flares while the X-ray telescope was looking at them. Some of them are variable in the optical. So what happened in those cases was, sorry here. What happened in those cases was that over time, and this is the optical flux, some of these are binary stars where the optical must have been observed somewhere there, somewhere at a low state where one was blocking the other. So if the optical is artificially low, then that push affects over F artificially high.
You tried removing those from the set and seeing if the line, like, maybe there's a very clear path above and below the black one.
There's enough of them that underwent an X-ray flare that it's still hard to remove all of those. And there's enough of those where there isn't enough information in the X-ray to determine how like significant the flare was.
So one way that the way you plotted the gray points, there's no sense of saturations or contours could help see if there's a lot of stuff above that line or not a lot.
Yeah, that's right. That's a good point. That's a really good point. The other thing, so another way to sort of plot all of this is to look into variability metrics in both the optical and the X-ray. And what you'll notice on the left, so red is whether there's a flag, it's determined to be X-ray variable, blue if it's not. Most of the X-ray variable things are indeed clustered right below that theoretical line. And I guess, yeah, contours of that would also kind of show what that, like how many points actually reach above that cut. It's a little trickier in the optical, where optical variables, for the most part, right, they do reach that cut and they get above the cut into this other one. But the most variable things, those are all up there. But this one, so this plot, I haven't shown too much because I've been wanting to try to interpret it myself as well. Hard X-rays, typically, it depends who you ask, it depends what X-ray telescope you're looking at. Typically, they're above, 1 keV, 2 keV. Some people say above 10 keV is a hard X-ray. But what I'm plotting here is a hardness ratio, which is the ratio of hard X-rays divided by, so I think this one is the flux of hard minus soft divided by hard plus soft. So, and then the whole range is 0.2 to 10 keV, where the break is roughly 2 keV. All of the sources below the cut tend to be softer, except for the symbiotics. Those tend to be harder. Anything above the cut tends to be harder as well. So this is, and in this case, the theoretical cut seems to work pretty well. Like you stop seeing blue sources above that. So these flares are not supposed to be particularly hard, which makes it all the more puzzling. Like why aren't you seeing the break here, but you are there? So I don't have a good answer. Aside from these two things, so there's two other problems with all of this that I've been thinking about recently, and one of them is, is there a radio main sequence? This X-ray shows a nice sort of clear clustering, but then my goal was to say, okay, is this possible in the radio as well? Just for galactic sources, just for galactic systems. So in at least for galactic objects, and one can have jets produced by young stars, and X-ray binaries. Those emit synchrotron radiation, which goes all the way down to the radio. Magnetic activity also from young stars and active stars has free emission. If there's a magnetic field, it'll have electron and cyclotron maser emission. That just means that the characteristic magnetic field for a lot of these stars is about 1 kilogauss. So the characteristic frequency of those electrons gyrating around a 1 kilogauss field will be seen in the radio. So this is getting back to that question, how do you know if an association is real when you just cross-match any two catalogs? And there's two things to consider here. The first one is just the probability that the source in catalog A is also detected in B. This assumes that the source is in both catalogs, though. What do you do if you have something in A, but there's just no corresponding source in catalog B? The next thing that one can consider then, if you don't want to make that critical assumption, is, okay, just what are the number of chance associations given some radius across matching? So these equations here kind of summarize what I wanted to say. Someone really looked into all this very, very deeply for their PhD. And what you effectively get is, if you begin with a Gaussian distribution of one of the sources, just what it would look like on the detector, then this probability that the source in one catalog is also in a separate one is something called a Rayleigh distribution. So it's just a Gaussian times R. The number of chance associations then is a lot simpler. It's just, what is the number density of sources, just n over the overlapping area, times your cross-match area. So this is what the basically the sum of the two distributions should look like. The probability of a real match, and this is just, let's say the sigma, just the point spread function, is the 1 arcsecond, is going to be the black curve, which begins down here, peaks up there, and then it goes to 0 basically. So yeah, the peak is roughly at a 1 arcsecond, whereas the probability of a coincidence match, it increases as a square, right? You just draw the circle bigger, the area will be bigger, so you'll encapsulate more sources. The sum of the two should look something like the blue curve. So what if you're taking any two catalogs and cross-matching them? You'll see a trade-off of those two distributions. What are the real matches, and then what are the chance matches? If you have a cross-match that's dominated by fake associations, it'll look like a square. And if you're dominated by real associations, it'll look like a Rayleigh distribution. Great. So by the way, if you take that the X-ray catalog, it'll look like basically like a perfect the sum of the two, because those X-rays were localized very well. I took the radio catalog, the newest catalog from the VLA Sky Survey, and cross-matched with an optical catalog, where the optical position is a lot better than the radio position. It's better than 1 arcsecond actually, compared to the 2 arcseconds of the radio. So just taking all of the matches, it looks super encouraging. And it's like, wow, okay, there's indeed this the Rayleigh distribution, and then it's not perfectly squared, but that's the tail end of the chance associations. When I then enforce the cuts that all of the objects are likely galactic, this is going back to Gaia, there's a proper motion and there's a parallax. So we know the distance is within the bounds of the galaxy. It looks like it's all fake cross matches. So this is really discouraging. And the reason behind this is that there's so many AGN, so many background AGN in the radio, that if you're just looking at an optical position in the sorry, if you're looking at a star in the galaxy in the optical, you have a high chance that there's going to be a radio source behind it. Right. So most galactic objects are contaminated. So to try to get around that, there's no, you can't just take, okay, let's just take all the sources there and hope that they're part of some distribution like that. That's not how that works. You have to assign a probability that it's a real counterpart or not. So these histograms look a little bit better. And the only way to make them to make these actually work is to enforce either an optical limit or a distance limit. And here, these plots can get a bit complex, but what I'm saying here is that from green all the way to pink, green is I'm just taking the optical source, I'm just taking the sources where the optical counterpart is brighter than 16th magnitude. And I'm walking in steps from 16 to 11th. These things are very bright. 11th magnitude stars in the context of optical astronomy are very bright. So you can see that at G equals 16, 15, 14, you're still totally dominated by chance associations. Only when you get up to G equals 11 or less than 11, do you actually get a nice peak. Already at 12, you can kind of see it. So one can then fit those distributions, fit that, plus the chance associations. Here, basically, there's, if you just look at the peak, this is a little bit above 0.1. This is 0.02. So 20% of the sources within that separation here will be fake. So 80% are real associations.
Can I ask why is it that enforcing cut on the optical magnitude helps if this is like a radio contamination effect?
Yeah, I suspect that the best thing to do is a combination of optical and radio, but there's so fewer optical sources that are that bright that there's no way that for those few sources, for every single one, you're going to have a radio thing in the background.
Yeah, I guess I'm confused why that affects the probability of having contamination. Like would the radio emission of these objects be like brighter than in Rivian, or is that not a thing? Like,
so yeah, the right way to probably think about it is that if there is another Lx over L bowl number, if there's like an L radio over L bowl number, there's also some characteristic like 10 to the 3 or whatever. The brightest optical sources would also have a bright radio.
okay.
So I think the faint end of the optical sources, the radio would be so low if this existed that they wouldn't be detected by that survey.
So like, do you go with the brightest, like if there are multiple radio sources that are consistent with an optical, to go for the brightest one, or?
There's usually never a case where there's many radio with an optical. Yeah. So this is just taking all the radio and then give me all the optical around the radio. Yeah. So that's a really good point. That helps me clarify a lot. If the reason why that might work is if there is some other sort of intrinsic relation like that in the radio. The plot on the right is then making a cut in distance. So it's similar where the more distant sources, they would have to be very radioluminous to be detected. The nearest sources here in blue would be, because they're closer, they don't have to be that radioluminous. So here you can see, indeed, if you put the cut at 200 parsecs, yeah, then there's a little bit more of a bump there, and the real associations actually come out. But that can still keep faint things that are nearby. So what I'm tentatively concluding here is that it's better to enforce a magnitude limit rather than a distance limit to maximize your chances of real cross matches. So what initially started as, these gray points that were initially, I thought, wow, yeah, these are all of the optical plus radio points. These are all the optical ones that are galactic. Really, the ones, if I just take G is less than 12 and just the points here within 2 arc seconds, you just end up with the red. This is a very tiny sample. It's like 200 associations. So it's very low, but they're very high confidence points for the reasons I stated before. And I only kind of see like, so then this is making an analogous radio main sequence, the same ratio on the y-axis, and then an optical color on the x-axis. There's still sort of a spread. So I don't think there's quite an LR over LOpt relation like there was in the X-ray. You can see that for the most part, active binaries, which are indeed radio sources, for the most part, they're only within one order of magnitude, between 10 to the 7, 10 to the minus 8. What's interesting about this sample is that there's so many of these sources over here, which appear to be some distinct class. Like there's no classification for these sources in any known catalog. They're just stars that have a high confidence radio association. So I'll be looking into those and seeing exactly what they are, but it's a little discouraging that it's this small a sample that actually came out of that. So I'll end here, and just some open questions are, how to construct an ultraviolet main sequence. I'm going to go about it basically the same way. There can also be a lot of background UV from galaxies, distant galaxies that can contaminate. And then the main question that I want to get at is, this radio survey, the VLA sky survey, these 1.6 million objects are just the first scan of the sky. It's actually done 2 more full scans of the sky that can be added and make a much deeper catalog. So that should increase. Yeah.
Oh, sorry.
Okay. It's all good. So that'll just increase the number of radio sources that'll be available to cross-match. With more than 100-ish sources, then I can say, okay, give me all of the X-ray plus optical plus radio. And my hope is that, if it's very difficult to initially say, yeah, here's a radio position, here's an X-ray position, if there's an optical one right there, then having the overlapping Venn diagram, that'll be like a clear sign, okay, all of these merge, that's the real counterpart. And literally just removing the X-ray, there can be all sorts of other optical sources in there. So I think the 3 survey cross-match problem, I haven't seen much on it in the literature other than for single sources, but doing that in a systematic way, I think might actually make it easier. Yeah, that's all I have. Thanks for your attention, and yeah, ask questions. Yeah, go ahead.
Yeah, so either, I guess, for the cross match, the 2 surveys, either like optical and X-ray or optical and radio, do you think that there have been, like basically based on what you're finding, do you think there have been cases like in the past where people have kind of presented some sort of statistics or some sort of scientific conclusion where it's been like contaminated a lot by faulty matches, by fault associations, based on what you're finding? Because it seems like basically you're showing this kind of more recent result, which is the histogram of the 2 different distributions that was from like a pretty recent thesis. So
yeah.
From like before that, when I assume people have tried to do radio optical associations, it seems like they might not have had the correct statistics on what the associations were.
That's a really good question. I don't know too much about the radio in the past, but I know in the X-ray in the past, one other really good metric is that variability. So the variability in the optical. So at least for all of the sources, all the sources up there, they're highly variable in the optical. If you have like 20 optical sources within one X-ray point, if you just select the most variable optical source, that'll most likely be the right cross match. But it was so difficult to do that in the past. I don't know if there were the big enough statistical samples of galactic objects. Probably for extragalactic objects there were. But for galactic objects, I don't know. Yeah. But that's a good point to look into. What if all of those things were just wrong? All those survey results in the past were just wrong.
Well, I don't mean like the survey, like, I don't mean like, I mean like, if there's like a scientific conclusion that's presented and, not necessarily like, here's a distribution of sources, but like, I don't know what people do, like, with the distribution of sources that we've associated with these two different bands, this is the science we can do from it.
Yeah. Something, just as an example of one paper that I've been, or one series of papers that I've been wrestling with, there's something that people can do in the gamma ray plus X-ray plus optical. And gamma ray is even harder than X-ray, where the circles are really big. And they notice one thing in the optical that's like variable. So this is in the gamma ray, that's in the optical. And then they point an X-ray telescope at it, and there's the X-ray. So they say, okay, the optical is roughly within the X-ray, which is within the gamma ray. That's the right cross match. But they just pointed the X-ray there. There's actually all these other X-ray point sources that also have optical point sources within them.
That aren't necessarily variable.
Some that aren't, some that are. So knowing what the right, like, I don't doubt that that's the right optical for that X-ray, but whether that's the right optical for the right X-ray, for the right gamma ray, I think that's a little harder to 100% pin down. Yeah.
So it seems for some of those cross matching things where you have like the initial peak and like the increase due to like false associations, like they're not really like quadratic in the right side. Like, do you know why that might be? Like they're more linear looking.
Yeah, they do look very linear.
I did have a question about that as well, which is related, is like, so this like quadratic curve is basically just adding up, like, is summing over like a uniform sort of distribution, right?
Right.
But if I like, do that and like, there are two objects
Yeah.
that within that radius, then that should only count as one cross match, right? So do we get a departure from quadratic because of that?
If you
Because otherwise, like, the probability is gonna go above one, right? If you continue to go quadratically.
You're plotting the separation to the nearest source, but so it's gotta turn over. Because you're gonna eventually, they always become a source.
Like if I
Right.
draw the circle really big and there are like 5 sources, that counts as one cross match, right?
Mm.
5.
yeah, that's a good question. So this is plotting the distribution of all sources, not just the nearest source.
Okay.
Yeah,
So it is interesting that they.
yeah. But yeah, you're exactly right. If I just get the nearest one, yeah, it does turn over. This is all sources. Yep. Sorry, I didn't quite end. What was your question again?
There's so many sources being like, it's like plotted 1 to the 10 to the 4 that like you would expect, statistics like follow like that perfect like parabolic curve
Yeah.
better.
Yeah.
Kind of weird.
Yeah, I think. Why would it not be quadratic?
Like, I would think that if you had like, if one source being there made it hard to see other sources, then it should be the other way. But I don't understand why it would be more likely. Yeah. Maybe you have thoughts about it.
The really unlikely scenario here is that, I mean, you'll see. I was gonna say that, you'll see that this kind of continues. So maybe this tail is an underestimate, and there could be more real associations that are like this far away, that are continuously bumping this up there and not bumping it up there. But I don't think that's good enough, like especially like for this whole long-term trend. And as you say, yeah, there's 10 to the 4 sources, that should be enough to reveal, to show the agreement with that. That's a really good question. I don't know. Yeah.
Separate question, for the color magnitude plotter.
The radio one or the X-ray one?
Actually,
Yeah.
yeah, where did AGN show up on that?
They're all up here. They're all up there. And this was impossible to make before Gaia. Because it was before Gaia, people made versions of this and said, okay, all of the extragalactic things are up there. All the stellar sources are there. But now with Gaia, now that we have distances, we can basically take out all of the, like separate the two. So yeah, all the time. For either side, whichever side, yeah.
Naively, okay, actually. I think, okay.
Yeah.
I was gonna ask, how did they know what CVs were, but I think the name, it's in the name.
Yeah.
Yeah.
Why could you not do this with AGN before Gaia? Couldn't you follow the optical source? Like, could you not get the same source?
It's a lot more AGN than these things, so you couldn't find these things. It's all AGN.
Exactly. So there were like thousands for every like 10-ish sources, or even one source. And
But
the
even
catalogs
the
as a whole.
top left, which is pretty empty.
Yeah.
Thank
Yeah.
you.
Thanks, Dan.
I have to run.
Appreciate it.
Yummy.
Thanks. So yeah, that was, yeah, it was just overly contaminated by the other sources.
I have a stupid question.
Go for it. Sure, it's not.
In high school, I've learned angular resolving power of a telescope is proportional to wavelength divided by diameter. And why the X-ray localization is over than not? Because I guess the order of magnitude in diameter of these detectors might not be as severe as the wavelength difference, right? So like, what's the limiting factor here?
Yeah, it's just a technical issue. It's just the making the detectors. The issue is that no X-ray telescope is diffraction limited. So it wouldn't follow that, because you have to focus the X-rays. Because X-rays are such high energy, what you need is grazing optics. Because if you have an X-ray mirror, like an optical, you can have a mirror, the optical light comes in and bounces off. For the X-ray, it'll go right through. So you need to literally go like this, where the angle of incidence is so small that it can actually graze and start to focus. Yeah.
It's technology.
It's technology, yeah. That's what it is.
Might be more severe for that.
That's why it's so big. It's such a huge, even bigger circle for gamma rays. Yeah.
What I find even more surprising is the radio stuff. Yeah, that they look like so well. I mean,
So are those diffraction limited then?
And radio, it's even better because you can combine multiple telescopes as an interferometer. That's what was used for that survey, at least. And there, you just have a huge collecting area, effectively.
most of the radio only where they sort of combine multiple telescopes throughout the earth and sort of form the big antenna.
Yeah, that's insane. That's the very long baseline interferometry. The data processing for all that is really hard, but they do that.
That actually go lesser. Credits for radio show.
Okay, any other questions? All right, let's thank our speaker again.
Thanks.
Thank you. Feel free to have some pie.
Thanks. Yeah, no, and thank